today's lesson. So next lesson on differential equation. Okay, let's just review some things first. We've lost Het completely, haven't we? Let's see what Het's saying. Oh, here he comes. Okay. Devansh, we started integration on the A-level classes. That's the Saturday classes. So we did our first lesson on integration last weekend, but that's really the basic integration. That's just where you do just like simple integration by recognition. But from this weekend onwards, we do the more sort of complicated integrations. But the last weekend's lesson is on YouTube. So you know when you go to the YouTube, the Math School, wherever I put the Math School channel, and you see like some of the video. So it is on there. So you can just find it there. Last weekend's lesson is on there.
Is this week's lesson going to be there as well? So
it will be there, but you can attend the lesson if you want to, or you can just wait for the recording.
Sure. I've got mocks next week, so I'll see how it goes.
Yeah. All right, so you're just back in time. So we've just started the lesson. So we just started the lesson. So it's differential equations, and it's the follow-on lesson on differential equations. And again, yeah.
Very quickly, out of context, you know, from next week, because lockdown's about to end, can we do normal lessons?
Well, yes. So, well, the answer to that is I'm waiting for a response from Quainton Hall, because again, we tend to go with whatever their advice is, because they have much more, they have much more information than we do. So I'm waiting for. I've asked them, can we go back? And I haven't had a response from them yet, so I'm just waiting for them to respond. Obviously, you know, I desperately want to go back into lessons because I'm suffering health problems trying to teach online. But do you find it that much worse, the online thing? Because there are some advantages to online thing. Like, for instance, I can record the lesson and then you can replay it and watch any question that you miss.
It's hard to concentrate, sir, for a long time.
Is it?
Yeah, but when you're looking at the screen.
Okay.
So you know the recording bit?
Yeah.
What our school does, it records the lessons anyway, so like you can create a team, like a meeting, and then you could just record the lesson.
Yeah, I can't do that in Quainton Hall School, and the reason I can't do that is because they're not my computers, so I can't set up anything. I can't put any software on there to record the lesson. So theoretically, what I'd be able to do is that I would be able to have some screen recording software, like on my computer here. I can record this lesson. I'm recording on Zoom, but even if I wasn't doing it on Zoom, I could just put screen recording software on and record the whole screen, or record just the bit of the screen that I want to record, and then do that. But I can't do any of that on their computers. I cannot edit any of the software on their computers. It doesn't allow me. I can't even put Zoom onto their computers because I don't have authority to do that. So my login only allows me user access. It doesn't allow me administrator access, so I can't change anything. And again, with your school, what they've done is they've probably edited the IT manager has put in all the extra software for the teachers to use. So it wouldn't be possible when we're at Quainton Hall. Unless I bring in my own computer and start using my own computer in the lesson, which might be an idea. Okay, so I'm going to go back over some preliminary knowledge that I just need to check you know how to do. You should already know that when you integrate 1 over 1 plus x squared, that gives you arctan x. So that's arctan x. And we learned that by using the substitution. We learned that x should be tan theta. If you replace x with tan theta and you use integration by substitution, you learn that integration is just arctan x. If I want to integrate this, the answer is just going to be arc sine x. And to do that, I would use the substitution x equals sine theta. I'd replace x with sine theta, and use integration by substitution, and it would work out nice and simply to just give me arc sine x. If I want to integrate something like this, I need to adapt my substitution a little bit. I can't just use x equals sine theta. So my substitution isn't going to be x equals sine theta. What's it going to be in this case? What am I going to replace x with in this case here? To Shane.
I remember the rule that we did last year was like x is equal to a over b sine theta.
Yeah, so because this has got a 9 in front of it, you want to get rid of the 9 when you put in whatever you put in here in x. So I'm going to put divided by 3. And the reason I'm going to put in divided by 3 is because when you square x, you're going to get a divided by 9 on there. So that's going to get rid of the 9 from there. Why do I want to get rid of the 9? Because I want to make it a 4. Why? Because then I'd have 4 minus 4x squared. And 4 minus 4 sine squared theta is 4 cos squared theta. So I'm going to put in a 2 on here. And the reason I'm going to put in a 2 on there is because then when I square it, I'm going to get x squared is going to have a 4 over 9 on there. The 4 over 9 is going to multiply by the 9 to give me 4. So x is going to be 2 over 3, and then it's going to be 2 over 3 sine theta. And so when you substitute it in there, you're going to get 4 minus 4 sine squared theta, square rooted, integrated. You're going to get a 2 on the top, but you're going to have to replace the dx as well. And the dx by d theta is going to be 2 over 3 cos theta. So you're going to get times 2 over 3 cos theta d theta. And the 4 minus 4 sine squared theta just becomes 4 cos squared theta. Just becomes 4 cos squared theta. But then we're square rooting it. So that just becomes 2 cos theta. So that just becomes 2 cos theta. And then the 2 cos theta, that and that and that and that cancel out. So all we're left with is 1 over 3 d theta. Oh, there's a 2 here as well. That's because there was a 2 on the top there. So 2 lots of 1 over 3 d theta, which is going to give me 1 over 3 theta times 2. So 2 over 3 theta. And then I'm going to replace the theta with, well, let's make theta the subject of this. Take the 3 there, take the 2 there, and inverse sine, arc sine. So it's going to give, yeah.
Why does it say times by 2 over 3 cos theta, and then you crossed it out?
Because let's go back a step. Whoops, let's go back a step. Okay, so what we had here, all I've done so far is I've replaced the x with 2/3 sine theta. And then that's given me square root 4 minus 4 sine squared theta on the bottom. But I also need to replace this dx. And to replace the dx, I need to differentiate that to get dx by d theta. And when you differentiate that, you get dx by d theta equals 2/3 cos theta. So when I replace the dx, I get 2/3 cos theta d theta. Okay, now this 4 minus 4 sine squared theta is just 4 cos squared theta. We know that. So that's just 4 cos squared theta. But it's being square rooted. And when you square root 4 cos squared theta, that just gives you 2 cos theta. So that just gives you 2 cos theta. But hold on, I've got a cos theta on the top of the fraction and a cos theta on the bottom of the fraction, so they cancel out. And I've got a 2 on the top here and a 2 there, so they cancel out. And the only thing I've got left with here is a 1 over 3, because that 2's cancelled out, and a 2 at the front here. So all I'm left integrating is integrating 2/3 d theta. So if you make the right substitution here for x, if you make the right substitution for x here, and you also remember to replace the dx, you'll only be left integrating a number here. You'll only be left integrating a number here. So I'm just left integrating 2/3 with respect to theta, which is 2/3 theta when you've integrated it. And then theta is 3 over 2 x inverse sine. So that gives me 2/3 arc sine 3 over 2x. The general rule, if you want to know it, is whenever you want to integrate 1 over square root a squared minus b squared x squared dx, the answer is just going to be 1 over b arc sine b over a x. That's the answer. If you want, just remember that. If you want, just remember that. If you don't want to remember that, just figure it out each time. It's not too hard to figure out each time. And the same rule would apply here, except your substitution would be not x is tan theta, like it was here, but x is 5 tan theta. Why? Because when you square 5 tan theta, you'll get 25 tan squared theta. And the general rule is when you want to integrate 1 over a squared plus b squared x squared dx, the answer is going to be 1 over ab arc tan b over ax. That's the answer, but you should know how to do it using the substitution. And so if somebody asked me to integrate this, I would say, that looks like that. All they've done is replaced a with c and n with b, and instead of having x as their variable, they've got y as their variable, which doesn't matter because they're integrating with respect to y anyway, so that makes no difference whatsoever. So my answer is just going to be 1 over n. So I'm following this pattern here, and my b is now n, so 1 over n arc sine n over c y, not x, because although that one's got an x in it, my variable here is y. And so it's 1 over n arc sine n over c y is my answer for that.
So I'm confused why you use 1 over b arc sine b over ax, because when we did the substitution, wasn't it just root a over root b sine theta?
No. Okay, so hold on. Let's just go back a second to here. Okay, what do you think a is here?
4.
No, a is 2.
Oh, you root it.
And what do you think b is here?
3.
Yeah. Okay, so that solves the root problem. Sorry, I have to go 1 second. Somebody at the door, and Mena's not here. Okay, I'm back. Okay, so it was just trick-or-treaters. Very late for trick-or-treating. Okay, so no, it is this is exactly the answer we got. Apart from the fact that ours has got a 2 on the top of it, which did change everything. We got 2 over 3, and remember RB is 3, so we got 2 over 3 arc sine 3 over 2x, which is exactly what we got. These numbers will usually hopefully be square numbers anyway. They'll usually hopefully be square numbers anyway. Okay, right. So in the June 2020 paper, the answer to question 7b was this. But Shruti's answer was this. Does that mean she's flopped it? Answer, please, Joanna.
Does B and A mean anything, or are they just random letters?
They're just constants. They're just constants. Like maybe she did an integration to get the answer.
Then yeah, I think it's wrong.
Why? Does it matter that instead of having A, she's used B as her letter for her constant. Does that make any difference?
Yeah, but then she's also used sine instead of cos.
Yeah, I know, but I'm asking specifically about whether if you use A as your constant or B as your constant, does that matter?
If they represent the same numbers, then no.
Yeah, well, we don't know what the constant is, so it's an unknown constant. So they represent the same unknown number. It's just somebody's used the letter A and somebody else has used the letter B. Does that make any difference?
No.
No. Okay. And so again, this choice of letter here for the N, well, that's the same, so that's not a problem. But this choice of letter here is different. But the choice of letter in itself makes no difference whatsoever. The fact that you've used an epsilon and somebody else has used a C makes no difference whatsoever. You're saying the problem is that she used sine. But hold on a second. If you take the sine graph and you shift it, if you do sine x minus...
because cos is the same as like sine, but just shifted.
Yeah. So if you do sine x plus pi over 2, then you'll be shifting this graph. You'll be shifting this graph by 90 degrees to the left.
But then wouldn't that mean that C is different to epsilon?
Yeah, but who cares? Nobody knows what C is and nobody knows what epsilon is. So yes, her C will be different from our epsilon, but it will still represent the same curve.
Okay.
Yeah. So actually it doesn't matter because this epsilon can absorb the constant and allow for it to shift left or right, then you can write it as sine instead of cos. So no, she hasn't flopped it at all. Okay, one more thing. What's the distance from A to B? What's the distance from A to B? And I mean the distance along the arc here. I mean that radial distance there along the, oh gosh, look what it's done. I don't want that. Daft computer. I want to go along the arc. Okay, what's the distance along that arc? Devansh. Formula for the length of an arc?
0.5 times theta.
Arc equals r theta, and the arc is the distance that we're referring to. Now, if it's moving like this, is the radius changing as it's moving?
No.
Is theta changing as it's moving? So if it stops here and then it carries on here, is theta changing all the time?
No.
Like for instance, when it gets to B, then theta will be there, but along the way here,
oh yeah, it would change. It would change.
Yeah, so theta's slowly increasing until it reaches this particular value of theta. And so if that's the distance, then if we differentiate that, then the velocity would be r d theta by dt. Whatever the rate at which theta is moving would give you the velocity. And if we differentiate it again, the acceleration would be r d2 theta by dt squared. So if I tell you, oh, it's moving at a constant angular velocity of 0.1 radians per second, you could do 0.1 times 0.5 will give you the velocity that it's moving at, the radial velocity that it's moving at, not the angular velocity that it's moving at. And similarly, if I tell you its velocity is changing, its angular velocity is changing all the time, and I give you an equation for the angular velocity, if I say theta equals t squared, then you could differentiate that equation and you could find d theta by dt, and then you could differentiate it again, you could find d2 theta by dt squared, and that will give you the acceleration. So you would know the angular acceleration, and then by multiplying it by r, you would know the radial acceleration. Okay, right, some more stuff. How do you differentiate implicitly? So I'm differentiating this with respect to x. So that gives me dy by dx equals 2, because that's just an x term, so that just differentiates normal, minus dz by dx. So there's my implicit differentiation. You do one, and here let's assume that v here is a variable, not a constant. So let's assume that's a variable, not a constant. You differentiate this one, differentiating with respect to x, Joanna?
So it'd be dy by dx equals minus v to the minus 2 dv by dx.
Lovely.
Times by minus 1.
And then subtract 1. Okay. Next one, differentiate this. Again, we're differentiating with respect to x. Differentiate this one.
That would be 8.
Start with the left-hand side.
So it'd be dz by dx is equal to 8x plus 6y dy by dx.
Lovely. Next one, Devant.
That would be dv by dv over dx equals.
What happens when you differentiate dy by dx with respect to x?
To get d squared y over dx squared.
d2y by dx squared.
Minus k dy over dx.
Lovely. Next one, to Shane.
dz by dx.
Oh, you're gonna have to use yeah.
So differentiate the first one, so 1 multiply by the second one, dy by dx,
Yeah.
plus x d2y by dx squared.
Yeah. And then you go.
Then plus dy by dx.
Oh, so plus another dy, so I can just sneak a 2 in there. So x d2y by dx squared plus 2 dy by dx. Next one, Joanna.
d2y by dx squared is equal to, and you have to do product rule.
Okay,
So then it
hold on,
would
let me
be
just highlight them. Okay, go for it.
minus x to the minus 2 times d2y by
Hold on,
dt
if you
squared.
differentiated the first one, then you
Yeah, you leave alone the second one. Dy dt, and then plus 1 over x times d2y by dt squared.
but we're differentiating with respect to x, so it would be d2y
Oh yeah,
by dx dt, because there's already a dt there, but we differentiated with respect to x.
Okay.
You might say, oh, that looks a bit rubbish now because we've got a dx and a dt in there, and we can find a way of like replacing it later on. But for now, that's the correct differential with respect to x. Differentiate this one twice, Devansh. So v here again is a variable, it's not a constant.
Sure. So that would be d squared y over dx squared.
Yeah. dy
So
by dx, sorry, to start off with. dy by dx equals. So you're just doing the first differential.
So that would be use product rule, right?
Yeah.
So
Differentiate the first one.
would that be v over x?
No, you're differentiating v, but you're differentiating with respect to x. dv by dx.
Oh, okay. Times e to the x.
Times e to the x plus,
And
now
then
differentiate the second one, multiply by the first one.
E to the x times v.
Okay, I'm going to factorize the e to the x out from there. So that gives me e to the x, v plus dv by dx. And you've got to differentiate it again So d2y by dx squared equals, go for it.
So that would be using product rule again.
You'll have to use the
So,
product rule again. Go for it.
So that would be e to the x times dv vt over dx.
Are you doing differentiate the first one and then multiply by the second one, or are you starting with differentiate?
I'm differentiating the second one, multiplying it by the first one.
So if you differentiate v with respect to x, you get dv by dx.
dv. Yeah.
And if you differentiate dv by dx with respect to x, you get?
You get d squared v over dx squared.
Lovely.
Plus e to the x times v plus dv over dx, yeah.
And again, we can factorize the e to the x out from there, so that gives us v plus 2 dv by dx plus d2v by dx squared equals d2y by dx squared. Okay, one more to Shane.
dv by dx.
Yeah.
And then
Sorry, I'm just trying to do my highlighting and I'll catch up with you. Okay, dv by dx equals, Karen?
minus p e to the power minus px
P e to the minus px
multiplied by y plus dy by dx
Yeah.
e to the minus px.
I'm going to factorize the e to the minus px out from there. So that gives me dy by dx minus py is
And then
dv by,
differentiate again.
then we need to differentiate it again.
d2v by dx squared
Smashing. Carry on.
is equal to minus p e to the power minus px multiplied by dy by dx minus py plus e to the minus px multiplied by d2y by dx squared minus p dy by dx.
dy by dx. Okay, so that gave us let's just have a look at that. So we got differentiate the first one, minus p e to minus px multiplied by the second one, plus differentiate the second one, which was dy by dx multiplied by the first one. So we factorize the e to the minus px out from there. So that gave us the dy by dx minus the py. And then we're doing the same thing all over again. So differentiate the first one, minus p e to minus px, dy by dx minus py. And then, so now we're going to factorize again the e to the minus px out from there. And so that's going to give us e to minus px. It's going to give us d2y by dx squared. That's that one there. It's going to give us minus p dy by dx, but this is also a minus p dy by dx when you've multiplied that out. So minus 2p dy by dx. And then the last term here is this one here, which is the minus p times the minus py. Remember, I'm leaving the e to the minus px out. So that gives me plus p squared y equals d2v by dx squared. Now I'm going to keep this result because we're going to need it later on. So I'm going to keep this result. I'm going to write it down on a separate bit of paper here, and I'm going to keep it for later on. So I'm going to write d2y by d2v by dx squared equals, that says d2y, doesn't it? I should say d2v. d2v by dx squared equals e to the minus px d2y by dx squared minus 2p dy by dx plus p squared y. So I've saved that on a piece of paper, and if we need it ever again, it's there for us. Yeah. Okay. Right. Oops, almost dropped everything. Okay. Right, second order differential equations. So second order differential equations are going to contain d2y by dx squared in them. So this is a first order differential equation. It doesn't contain d2y by dx squared in it. This is a second order differential equation. It contains d2y by dx squared in it, and it contains a dy by dx in it. A second order linear differential equation would not contain any y squareds or y cubes in it. So this doesn't contain any y squareds or y cubes in it. This doesn't contain any y squareds or y cubes in it. So there'll be linear differential equations. Okay, so the first type of second order differential equation that we should be able to solve is a direct one. A direct one is effectively one that an A-level student can solve, because all you do is get all the x's on the other side of the dy by dx, and then you just integrate it. So here, all I'm going to do is write d2y by dx squared equals 2 over x. Then I'm going to integrate it. When you integrate d2y by dx squared, you get dy by dx equals 2 ln x plus c. I'll just put the plus c at the end instead of the a, which I would normally do. And then all I need to do is integrate it once more. Integrate it once more, and that's going to give me y equals, oh crap, what's the integral of ln x? Do you know that?
1 over x. Oh, no,
that's differential of ln x. We learned the integral of ln x using parts. Go for it.
Is it x ln x minus 1 plus c?
It's x ln x minus x plus c, yeah. So the answer is going to be x ln x minus x, but there's a 2 in front of all of this, so I'll put a 2 in front of that. And then plus cx, because we're integrating this, plus cx plus, I can't use c, I'll have to use d now. Okay, so that was easy. That was just integrating twice, nothing harder to that than this. Same sort of situation here. We can rewrite this as d2y by dx squared equals x cos x. And then now we can integrate both sides. So that gives us dy by dx equals, if I'm integrating this, I might use parts. Leave alone the first one, integrate the second one. So that gives me x sine x minus the integral of differentiate the first one, integrate the second one, minus the integral of sine x, and integral of sine x is minus cos x, so plus cos x plus c. And then I'm going to integrate it again. And so that gives me y equals, oh no, I'm going to have to use parts again. Leave alone the first one, x, integrate the second one, minus cos x, minus the integral of differentiate the first one, which is 1, integrate the second one, which is minus cos x. So I've just got to integrate cos x, which is sine x plus sine x. And then I've got to integrate cos x again, which is another sine x plus, and I've got to integrate the c, which is cx plus d. And so there's my, all I've done is integrated twice. You notice you get 2 constants. You get a constant here, and you get another constant here. Every time you solve a second order differential equation, unless they give you numbers to put in, you're going to end up with 2 constants. Okay, right. Those are the easiest ones, and those are ones that an A-level student can do. So they're nothing to do with further maths at all. What if we have one that's exact? Well, this is identical to what we were doing last week with first order differential equations, except we're just doing it with second order differential equations. So when you differentiate, let's get the terms in order first of all. Let's get the dy by dx, the d2y by dx term first, then the dy by dx term, and then on the other side will be all the x terms. So let's rewrite that as x squared d2y by dx squared plus 2x dy by dx equals 2 over x squared. Okay, let's see. If you differentiate dy by dx, then that gives you d2y by dx squared. Yeah, sure. And if you differentiate x squared, then that gives you 2x. Yeah, sure. Okay, so somebody's used the product rule. What did they start off with? They started off with x squared, the front of this arrow. And they started off with dy by dx, the front of this arrow. X squared dy by dx equals, and then integrate this, because effectively I've integrated this. I've unproduct ruled it, which means I've integrated it. equals integrate this, which is going to be 1 over x. Well, no, 1 over x would give you minus 1 over x squared. So it's going to be minus 2 over x. Minus 2 over x is going to give me 2 over x squared when I differentiate it. Add a c, plus a constant. Okay, now let's make dy by dx a subject. Dy by dx equals minus 2 over x cubed plus cx to the minus 2. And then let's integrate it once more. Y equals, so that's going to be 1 over x squared, which when you differentiate it, it does give you minus 2 over x cubed, plus c over x, which when you differentiate it gives you minus c x to the minus 2. So really that should be a minus in front of there, but I'm not going to bother by changing the minus because it doesn't make any difference. Plus d. So there's my answer. Really, I should have changed that to a minus c, or if I want to leave it as a plus, I should change it to a plus e or something like that, really, strictly speaking. I'm going to be absolutely pedantic about it. Okay, so this is again an exact equation. Let's rewrite it. Let's rewrite it as y d2y by dx squared plus dy by dx times dy by dx equals cos x. You can see that they started off with dy by dx, and that differentiates to give us d2y by dx squared, and they started off with y, and that differentiates to give you dy by dx. So that means we know that they used the product rule, and they started off with y and dy by dx, and then they got that when they differentiated it. So now I've integrated it, equals, and then if I integrate cos x, that gives me sine x plus c. Okay, now I've got a differential equation, but my variables are already separated. My y's are on the dy by dx side and my x is on the other side, so I can just put an integral in front of both sides, an integral and an integral, maybe take the dx up here, and so that gives me a half y squared equals integrate sine x is minus cos x plus integrate c is cx, and I need a new constant d. And so there's my answer. Maybe I should multiply it through everything by 2, and then it will look nicer. Y squared equals d minus 2 cos x plus cx. Strictly speaking, I should have changed the d to an e, and I should have changed the c to an f because I multiplied them by 2. But I don't know their numbers anyway, so I'm not really fussing about it too much. Okay, same thing, but now using an integrating factor. Again, this is identical to what we were doing last week. There's nothing different from what we were doing last week. Let's arrange our terms in order. So it gives us x d2y by dx squared plus 2 dy by dx equals 1 over x. Can you see what two things somebody must have multiplied together? Well, the dy by dx certainly matches with the d2y by dx squared, but this one does not work. The x does not differentiate to give me 2. So I need to use the integrating factor method. What I need to do is divide both sides by x, but I'm only doing it mentally. I'm only doing it in my head. I'm not physically going to do it. I'm going to divide by x. That's going to give me 2 over x. Then I'm going to integrate that. I want e to the power integral of 2 over x. 2 over x integrates to give me 2 ln x. So that gives me e to the 2 ln x. Move the 2 up here. Okay, I need an x squared at the front. I need an x squared at the front. The integrating factor tells me what I need at the front. I need an x squared at the front. At the moment, I've got an x. So I'm going to multiply by x. So that's going to give me x squared d2y by dx squared plus 2x dy by dx equals x. I've multiplied everything through by equals 1. I've multiplied through everything by x. Okay, does it work now? That differentiates to give me that. That differentiates to give me that. Yep, I can simply integrate this instantly now, and I would get Joanna.
You'd get x squared and dy by dx. x. What's the thing next to it? I can't. Oh, plus c.
Okay, and then now I'm going to divide through by x squared, so dy by dx equals 1 over x plus cx to the minus 2. And then I'm going to integrate, so y equals, integrate 1 over x, it gives me ln x. Integrate c over x squared, it gives me minus c over x. I'm just going to write plus c over x. I hope you won't mind. I'll put a constant inside here as well. Two constants because I had to integrate twice. Next one, again, let's put the terms in the correct order first. d2y by dx squared plus 2 dy by dx equals a half. What's my integrating factor going to be? What's my integrating factor going to be? You can do the whole integral of e to the integral of blah 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 gives you blah 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 gives you blah blah blah, and then just give me the final answer. What's my integrating factor going to be, Devansh?
So when you integrate dy by dx, you get d squared y over dx squared. But
No,
when you integrate...
No,
I'm just...
What are you talking about, Devansh? When you differentiate dy by dx, you get d2y by dx squared. Yeah, that's obvious. Yeah. When you differentiate dy by dx, you get d2y by dx squared. But this doesn't work. When you differentiate 1, you don't get 2. So that means we're going to have to use the integrating factor method like we use here. What I have to do is this x didn't match that 2. If you differentiate x, you don't get 2. So what I need to do is I need to divide by the x. I need to divide. Now really I'm supposed to divide through everything by x, but I'm only interested in this bit here, the 2 over x. So I'm not dividing everything through by x because I can't be bothered. So 2 over x, then I need to integrate the 2 over x, integrate 2 over x, and then I need to do e to the power of that. That's how you find the integrating factor. Exactly the same as you were doing on the homework.
Yeah, but in this one I was getting e squared, that's why.
Yeah. You're getting e to the
2.
No. What did you have to do here? Remind me again, what did you have to do here?
We did the coefficient of the d squared y over dx squared divided by the coefficient of dy by dx.
You got them the wrong way around, but yeah, 2 over x, yeah?
Yeah, 2 over x.
What did you have to do to the 2 over x? Two things you had to do.
You had to integrate 2 over x.
First of all, you had to integrate 2 over x, and then?
You did e to the power of that.
Right, that's how you find the integrating factor. Now use that same principle here.
Oh, okay, so you get, when you integrate 2, you get 2x.
Yep.
And then e to the 2x.
E to the 2x is the integrating factor. So we're going to multiply everything through by e to the 2x. So times e to the 2x. So that gives me e to the 2x d2y by dx squared plus 2e to the 2x dy by dx equals a half e to the 2x. Now everything should work. When you differentiate dy by dx, you do get d2y by dx squared. When you differentiate e to the 2x, you do get 2e to the 2x. So we know that somebody started with e to the 2x and dy by dx, and they used the product rule to differentiate to get to there. And so we've undone it, which means we've integrated. And we need to also integrate this, which gives us a quarter e to the 2x plus c. Then we can divide everything by e to the 2x, so dy by dx equals a quarter plus ce to the minus 2x. And then we can integrate once more. Y equals a quarter x plus, now that's going to be minus a half ce to the minus 2x. but I'm just going to call it de to the minus 2x plus e. Okay, and so there's our answer. And it's really no different from what we were doing last week. It's second order, but it's really no different from what we were doing last week. One more question. This time I've been really generous and I've given you the terms in the right order. So the dy by dx certainly differentiates to give you d2y by dx squared, so no problem with that whatsoever. But sine x does not differentiate to give you 2. So we've hit a problem, and it's a problem that only the integrating factor can solve for us. What is our integrating factor going to be? Work it out on your bit of paper now, and then just give me the answer. What is the integrating factor going to be? I can't see the yellow when I'm writing it. It's so faint. I get cosec x plus cot x to the power minus 2 because I had 2 over sine x. That was from taking the sine x down here. That gave me 2 over sine x. And I need to integrate that. And I know when you integrate 2 over sine x, well, I know 2 over sine x is 2 cosec x. I know when you integrate cosec x, you get minus ln cosec x plus cot x. And there was a 2 in front of there, so I got a 2. And then to get the e and the ln to cancel out, I had to move the minus 2 out of the way. Then the e and the ln can cancel out. So that gave me cosec x plus cot x to the minus 2. Now that looks quite messy, so I'm going to try and tidy it up. Cosec x is 1 over sine x. 1 over sine x. And cot x is cos x over sine x plus cos x over sine x, all to the power minus 2. Which is sine squared x over 1 plus cos x all squared. Ouch, that's a nasty integrating factor. Never mind, it won't trouble us, it won't bother us. Who cares if it's a nasty? We don't care. We're not perturbed by stuff like that. So our integrating factor is sine squared x over 1 plus cos squared x. That tells us what we want at the front. Okay, well, we've already got sine x at the front. So what we're going to need to do is multiply by sine x over 1 plus cos squared x. So I'm going to multiply by times sine x over 1 plus cos x squared. So that's going to give me sine squared x over 1 plus cos x squared d2y by dx squared plus 2 sine x over 1 plus cos x squared dy by dx equals 2 sine x over 1 plus cos x squared. So all I did was multiplied by the integrating factor. Now here's the interesting bit. This we know differentiates to give us this. If we've done the integrating factor correctly, then this should differentiate to give us this. What do? Do we trust the fact that we've done it correctly and just say, yeah, it works, who cares? Or do we need to check? What do you say, Shane? I trust you. Do you think we can just go with it?
I think we should check.
You think we should check? Okay, well, we'll check. I mean, I would have just gone for it, but if you think we should check, then it's probably safer to check. Okay, So what we need to check is when you differentiate sine squared x over 1 plus cos squared x, you do actually get this. And to Shane's saying, look, just check. It won't take you long to check. Just check. So we want to differentiate sine squared x over 1 plus cos x squared, and it should result in this. Okay. Can I just write it as being squared like that instead? And then use the chain rule. So you get, so I'm differentiating it. So it gives me 2 brackets sine x over 1 plus cos x to the power 1. Oh, but then I've got to multiply by the differential of the brackets. Differential, oh crap, I've got to use the quotient rule anyway. I thought, well, maybe we wouldn't have to use the quotient rule, but we do. Okay, so differential of the brackets, inside the brackets, is differentiate the top, which is cos x, multiply it by the bottom, 1 plus cos x, minus, differentiate the bottom, differentiate 1 plus cos x, it gives us minus sine x plus sine x, multiply by the top, that's another sine x, so sine squared x, all over the bottom squared, 1 plus cos x all squared. Oh crap, can we even read this? Okay, so it's cos x times 1 plus cos x, so that's cos x plus cos squared x plus a sine squared x plus sine squared x. Well, hold on, cos squared x plus sine squared x is just 1. So it's 1 plus cos x over 1 plus cos x all squared. Oh, look, that cancels down. So it's just 1 over 1 plus cos x. Oh, so this is just 1 over 1 plus cos x. And so if you multiply all of that together, it gives us 2 times 1 times sine x, 2 sine x over 1 plus cos x times 1 plus cos x over 1 plus cos x squared. Does it match? Does it match? Does it match? I can't remember. 2 sine x over 1 plus cos x all squared. Ah, it works. Phew! That's good. That restores our faith in the integrating factor method. Okay, so now integrating the left-hand side. What happens when I integrate this? To Shane.
It's dy by dx sine squared x over 1 plus cos x squared.
And the right-hand side? It's actually not that hard.
We just worked out that that's sine squared x over 1 plus cos x squared.
What Shane's saying is, look, we just said that when you differentiate this, it gives you this, and that is what we got here. So the integral of that must be that. So he instantly realized that actually we know it. The answer is equal to sine squared x over 1 plus cos x squared plus c. Okay, right. Let's divide everything through by sine. Let's get rid of this. Let's divide everything through by that fraction, sine squared x over 1 plus cos squared x. So that gives us dy by dx equals oh, well, that's just going to become a 1 plus c 1 plus cos x squared over sine squared x. Now we still need to integrate once more. So to integrate once more, well, the problem is not going to be integrating this. That's going to be easy. Integrating this is going to be easy, but integrating this is going to be a little bit of a mess. But actually, it's not going to be so bad because we can split the numerator. And when you can split the numerator, life is always sweet. So 1 plus 2 cos x plus cos squared x all over sine squared x is this fraction, which is 1 over sine squared x plus 2 cos x over sine squared x plus cos squared x over sine squared x is still that fraction, which is cosec squared x plus 2 cos x sine x to the minus 2 plus cot squared x. Right, now we're ready to integrate it. So, integrating the dy by dx gives us y. Integrating the 1 gives us x plus c times, all of this is times c. The c's in front of all of this. The c's in front of all of this. C times integral of cosec squared. Do we know the integral of cosec squared x? Anyone?
Of cosec x.
Squared x. Cosec squared x.
Mm.
Do you know the integral of sec squared x? Integral of sec squared x
is tan x.
Yeah, so
But
integral of
integral
cosec squared
minus
x
cot x.
minus cot x. What about this one? Well, we can try recognition. We can try sine x to the power minus 1. When you differentiate sine x to the power minus 1, it gives you minus cos x sine x to the minus 2. So all we need to do is multiply it by minus 2 times minus 2. And integral of cot squared x. Do we know the integral of cot squared x? Integral of cot squared x. Do we know the integral of tan squared x? Integral of tan squared x. How do we integrate tan squared x? We replace it with something. 1
Sine
plus tan
squared x minus 1.
Sec squared x minus 1. So how do we integrate cot squared x? We replace it with cosec squared x minus 1. And then integrate cosec squared x, we know is minus cot x. So minus
I got
2.
minus cot x minus x plus c.
Say that again.
Minus cot x minus x plus c.
For what? For what integral?
For cot squared x.
For integral of cot squared x? How did you do it?
I got minus cot using this method.
Using
Cosec squared x minus 1.
Okay. So you got minus cot x, and then you got minus x.
Minus x.
Minus x.
Yeah.
Okay, minus x. Okay. And so there's our answer. We can factorize the minus out from there. Maybe the minus could just be absorbed by the c, and then that could be a plus, and that could be a plus, and there's our answer. Okay, so they can be quite messy. Okay. Next situation is second order reducible to first, which is an example of substitution. Okay, and there are two situations. If we have one where x is absent, so if we have one where, well, let's do the first one. First one is where y is absent. If we have one where y is absent, so the whole differential equation does not contain y's in these bits here. There's no y. Okay, you can have a dy in the dy by dx, but there's no y's in these bits here. Then what we're going to do is we're going to replace dy by dx with p. And if you replace dy by dx with p, and then if you differentiate that with respect to x, then you get d2y by dx squared is dp by dx. So we can replace d2. So we use these two substitutions. This one and this one. So if I look at this one, I can see there's no y's in any of the yellow bits. So I'm going to use this method. So d2y by dx squared is going to be replaced with dp by dx. And dy by dx is going to be replaced with p. And everything else is going to stay the same. X plus 2 equals 2 over x. Okay. And so you notice y's disappeared from my differential equation. It's now got x and p in it. And if I look at this differential equation, I think, oh, this is nice. This is not so bad. Because this is an exact differential equation, or it's an integrating factor differential equation, because when you differentiate the p, it gives you dp by dx. And when you differentiate the x, well, it doesn't give you 2, but you could easily work out the integrating factor. The integrating factor would be 2 over x integrated, and then e to the power of that. 2 over x integrated is 2 ln x, and then e to the power of 2 ln x is, bring the 2 up, it's just x squared. Right, so I need an x squared at the front. Right, all I need to do is multiply by x. All I need to do is multiply by x. So x squared dp by dx plus 2xp equals 2. Now it should be exact. The p differentiates to give me dp by dx. The x squared differentiates to give me 2x. Oh, lovely. So that means x squared p equals, integrate the 2 gives me 2x plus c. Okay, now substitute back. What was p again? P was dy by dx. Replace the p with dy by dx. dy by dx times x squared equals 2x plus c. Let's divide through everything by x squared. So dy by dx equals, divide by x squared, 2 over x plus cx to the minus 2, and then integrate once more. Integrate once more. Y equals 2 ln x plus c over x plus d. Okay, so that was using the substitution where we replace, because there was no y's, we replaced dy by dx with p and d2y by dx squared with dp by dx. And it's logical because if dy by dx is p and you differentiate that with respect to x, you get d2y by dx squared would be dp by dx. Let's do another one like that. Again, you can see for this equation that there's no y's anywhere. There's no y's here, and there's no y's there. Ignore the y in the dy by dx and the d2y by dx squared, because that's obviously going to be there, but there's no y's anywhere. So we can use this method here. What will my differential equation become once I've used that substitution? Devansh?
Sorry, can you say that again, please?
I'm going to replace the d2y by dx squared with dp by dx, and I'm going to replace the dy by dx with p. What do I get?
You get 1 plus x squared multiplied by dp by dx.
Lovely.
Equals 2xp.
Lovely. Okay. Now I'm going to separate the variables. This is just separate the variables. This is just like an A-level student could do it. All the p's on the left-hand side, all the x's on the right-hand side. 1 over p. Whoops, I didn't want to do that. 1 over p. Whoops. Oh, okay. Let's just try and get rid of that e. 1 over p dp equals 2x over 1 plus x squared dx, and then integrate both sides. Integrate, and then what does that give me?
Sorry?
Integrate the 1 over p.
So that would be 1 over.
Everyone knows.
So it would just be minus p.
Okay, tell him what the answer is, Joanna.
Ln p.
Ln p. And integrate this one here.
2. So that would just be 2 arc tan x.
Tell him what the answer is, Joanna.
It would be ln 1 plus x squared.
Ln 1 plus x squared, lovely. And we need a constant. I'll put the constant in here. And then we can e to the power both sides, so that gets rid of the ln from both sides. So that gives us p equals a brackets 1 plus x squared. Have we finished? No, we use substitution. P stood for dy by dx. We need to replace it. So dy by dx equals a brackets 1 plus x squared. And then now we can integrate it. So integrate 1 dy equals integrate a 1 plus x squared dx. And so that gives us y equals a brackets x plus a third x cubed plus c. And so there's our answer. Okay, so that was when y is absent. What if x is absent? So look at this one here. There's nothing in front of the d2y by dx squared, in other words, just a 1. And there's only a y here. So there's no x's floating around in this equation. I'm not including the dx. I'm just looking for x's. So if x is absent, then I can use this rule here for x is absent. Now this is a slightly more complicated rule. This rule says if x is absent, then you're going to replace dy by dx with p. Then if you differentiate this, dy by dx equals p, you get so if dy by dx is going to be p, if you differentiate this, d2y by dx squared is going to be dp by dx. Now dp by dx isn't that useful to us, so what we're going to do is rewrite it as dp by dy times something. Now we know that we've got to end up with dp by dx, so that's going to have to be well, you're going to end up with a dy on the top here to cancel out with that dy, and you're going to end up with a dx on the top there equals d2y by dx squared. But hold on, dy by dx is p, dy by dx is p. So that gives you d2y by dx squared equals p dp by dy. You know what? It doesn't matter if you understood that or not. It doesn't matter if you understood that or not. Just remember that this is the new rule. If you're using case 2, when x is absent, the d2y by dx squared has to be replaced with p dp by dy, not with dp by dx, because then you'd introduce x's in and we're trying to get rid of x's. So, okay, so help me do this one. What am I going to replace the d2y by dx squared with, and what am I going to replace the dy by dx with? And so what do I end up with, to Shane?
P dp over dy plus y then p cubed is equal to 0.
Lovely. So all he did was said, oh, we've got a d2y by dx squared. Well, we're supposed to replace that with p dp by dy. It really doesn't work when you do the green highlighter and the pink highlighter as well. So all he did was replace that with p dp by dy. And then we also said we're going to replace dy by dx with p. So all he did was replace the dy by dx with p. Nothing more complicated than that. What do you immediately notice would be very exciting and tempting to do right now? What do you immediately notice would be tempting to do right now? Asking that to Devansh.
I was thinking of factorizing the p.
Divide by p. Yep, divide by p. I'm going to divide by p. I'm going to get rid of the p from there, and I'm going to get rid of the p from there. Nobody minds me doing that, do they?
Does it get rid of a solution though?
It does. What's the solution it's got rid of?
P equals 0.
And what did p stand for?
Dy over dx.
And if you solve dy by dx equals 0, what do you get? Integrate both sides?
You get y equals 0.
C. 0.
Oh yeah, sorry, my bad. Yeah.
So I've lost the solution. Y is a constant. Y is a constant is a solution to this equation. It's not a particularly interesting solution, but it is a solution. So in a homework, if I miss that solution out, that's a challenge, isn't it? If we're going to be pedantic about things. Okay, right, let's separate the variables. dp by dy equals minus yp squared. Minus 1 over p squared dp equals y dy. Integrate both sides. That gives me 1 over p equals a half y squared plus c. And replace back in what p stood for. What did p stand for? That was dy by dx. So 1 over dy by dx would be dx by dy equals a half y squared plus c. Okay, it's dx by dy, but that's okay because now I can still separate the variables. So take the dy over here, integrate. That gives me x equals 1 over 6y cubed plus cy plus d. There's my equation. Another one where we have y missing. Actually, we have x missing and we have y missing. So we could use either one of these methods. If you use this method, it will work lovely. If you use this method, it would also work lovely. It will give you exactly the same answer because y and x are both missing from that. So it doesn't make any difference which one you use. Well, let's use this one because that's the last one we've been using. We haven't had a lot of practice of it. So the d2y by dx squared is going to be p dp by dy plus 1 over 10 p squared equals 0. I'm going to divide by p, which means I've lost a solution. You're not going to have lost a solution. So that gives me dp by dy equals minus 1 over 10p. And then let's take the p onto this side. So minus 1 over p dp equals 1 over 10 dy. Integrate, integrate. That gives me minus ln p equals 1 over 10y plus c. Let's put a constant inside here. Let's take the minus across to the other side. Let's e to the power both sides. So that gives me, oh, I don't need the plus c because I put the a in. I didn't need the plus c because I put the a in, so I don't need both constants, just need one. So e to the power both sides, that gives me ap equals e to the minus 1 over 10y. Divide both sides by ap equals c e to the minus 1 over 10y. Substitute p was dy by dx. dy by dx equals c e to the minus 1 over 10y. Let's separate the variables again. So e to the 1 over 10y dy equals c dx. Integrate, integrate. That's going to give me, my guess is going to be e to the 1 over 10y. I'm going to have to times it by 10 equals cx plus d. And so there's my answer. Probably needs a bit of tidying up as well. But essentially, we've done that. Okay, this is really important. This is a really important situation. We're going to come across this a lot, although it won't be like this when we come across it. It'll be d2x by dt squared equals minus n squared x. But I'm hoping you'll see that that's exactly the same as that. All that's happened is we've swapped the y to an x and the x to a t. And then we've moved the minus n squared term to the other side. But they're essentially the same thing. But we're going to get it like this in future. It's going to appear like this in future for us. Okay, so, well, this one has got x absent, so we can use this method here. So we're going to replace the d2y by dx squared with p dp by dy plus n squared y equals 0. And then we can separate our variables. So p dp by dy equals minus n squared y. Take the dy up here, integrate both sides. That gives me, that's an easy integral, that's just half p squared equals, and then that's minus a half n squared y, minus a half n squared y plus c, plus c. Gonna multiply through by 2. So that gives me p squared equals c minus n squared y. I hope you don't mind, even though I multiply through by 2, I didn't change the c into a 2c or into a d, which is what I should have done. If you're going to be very pedantic about it, you would have changed it to a d, but I always run out of variables, constant letters for my constant when I do that. So I end up just saying I can't be bothered, I'm just going to leave it as c. I hope you don't mind. I'm going to replace the c with a c squared, which might be a bit of a problem if c turns out to be negative. Might be a bit of a problem if c turns out to be negative, but let's hope it isn't negative, in which case I can just, if I don't know the constant and I call it c squared instead, it doesn't really make much difference. Okay, and so that gives me p stood for dy by dx, so I can replace the p back with dy by dx. P stood for dy by dx, so dy by dx squared equals c squared minus n squared y squared, and so that gives me dy by dx equals square root of c squared minus n squared y squared. Separate the variables, so that gives me 1 over root of c squared minus n squared y squared dy equals
So,
yeah.
where did the y squared come from?
I was integrating both sides, so I had this integral of y dy. I mean, forget the n squared. You can ignore that for a second. I was just integrating y dy, and it gave me a half y squared. Because my variables were p and y. There was no x left anymore, so my variables were p and y, so I was integrating with respect to y.
Okay.
Separate my variables, so that gives me integral of that gives me integral of 1 dx, and then that gives me, oh crap, how do we integrate 1 over root c squared minus n squared y squared dy? How do we integrate that? Gosh, does anyone even know how to integrate that? Anyone on the planet?
Isn't that 1 over n arc sine?
Lovely. Very good.
one.
Okay. So, yes, we said that if you have integral of 1 over a squared minus b squared x squared square rooted, that's 1 over b arc sine b over a x. So this is going to be 1 over n arc sine n over c y equals, integrate this, it's going to give me x plus, let's not use the letter c, let's use d. Okay, right, let's multiply through everything by n. So that gives me arc sine n over cy equals nx plus, let's call this e, because I don't know what n is and I don't know what d is, so I might as well just call it e, just merge them together, call it e. Let's sine both sides, so n over cy equals sine nx plus e. And let's multiply both sides by c over n, y equals c over n sine nx plus e. You know what, I don't even know c and I don't know n, so I'm not going to call it c over n anymore. I'm going to just change that to, I don't know, a. Y equals a sine nx plus c. Now the beauty of that is it's a very simple equation. Y equals sine x is like this. It does one cycle in 2 pi revolutions. Y equals sine nx just is squashed by n. It's just squashed by n. So it does it n cycles in 2 pi, in a distance of 2 pi. A times that is just means instead of going from 1 to -1, it goes from a to -a. So this is really just a sine curve. It's just an yes, there's an e here, but we will often fix it so that e is 0. We will often fix it so that e is 0. So we won't even need to worry about this. That's called a phase shift. That just means instead of starting from here, we start from here. Yeah, but we're going to try and not have that. So this leads to the solution of this, which is, well, there's a name for that. It's called simple harmonic motion. Simple because it's the easiest thing in the world. It's just oscillating like this. Harmonic because it always keeps the same frequency. And oh, what's happened to our page? It's gone. And motion, because it's going to describe the motion of a particle. So right, so this is that. We did this one a second ago. Well, we didn't actually. We did d2y by dx squared equals minus n squared y, and our answer was a sine nx plus e. Our answer was y equals a sine nx plus e. The only interesting thing here is the n squared becomes an n in here. Everything else is just kind of as you'd expect. Okay, so now we're looking at this situation, which is going to be the situation we're going to come across more often, and the answer is just going to be exactly the same. It's going to be x equals a sine nt plus e. But because of the phase shift thing, if I shift this graph just a little bit, so this graph, if I just shift it a little bit like this, it becomes cos. So if you want, depending on what E is, you can change that to cos. If you change that to cos, then obviously you've affected this E. That E will have changed. It'll be a different. So I'll use epsilon instead now to say that the E's changed to a new letter, epsilon. So a cos nt plus E. So it doesn't have to be sine, it can be cos. So when I see this, all I see is, oh, right. So all you've done is you've made n equal to 3. Well, then the equation is x equals a cos 3t plus e. There's my answer. I don't even need to do any working. Solve my second order differential equation in less than 1 second. And if I see this, I say, oh, that's d2x by dt squared equals minus 4x. So n is just 2. So that's x equals a cos 2t plus e is my answer. And it's going to be simple harmonic motion. What do I mean? The normal simple harmonic motion does 1 cycle in 2 pi, but mine's going to do 2 cycles in 2 pi. It's going to go like that and like that. It's going to do 2 cycles in 2 pi. It's the same thing, but this time they've gone back to y and x instead of x and t, and n is 5. So it's going to be y equals a sine 5x plus e, or y equals a cos 5x plus e, depending on which one you happen to prefer at any particular moment. Okay, systems that give rise to simple harmonic motion. Here's a system that gives rise to simple harmonic motion. What you do is you have a spring, and then you attach a mass on the end of that spring. When you do that, the spring extends and it goes down to here. So when you do that, it goes down to here. So what I'll do is I'll get rid of that, and I'll extend the spring, and this is with the mass on it. It's already extended. Imagine it's already extended. Okay, that's its equilibrium position now. It's stretched the spring, but it's in equilibrium. Now what happens is Hep walks past my beautifully set up spring mass system, and because he's a bit mischievous, he pulls it down as he walks past it. He pulls it down to here, and then he lets go of it. So he extends the spring to here, and then he lets go of it. What you'll find is it does this. It oscillates backwards and forwards. That's simple harmonic motion. Another situation which will give rise to simple harmonic motion, but it's a slightly different situation, is I've got a string attached to the ceiling with a little mass attached to it. And then this time, as Joanna walks past it, she just swipes it with her hand like that. She just swipes it with her hand like that. And what it does is it starts moving. She displaces it and it starts. So what it starts doing is it starts oscillating backwards and forwards. That is also simple harmonic motion. The difference between Het's situation and Joanna's situation is Joanna cannot displace it too much, otherwise it won't be simple harmonic motion. If she really pushes it hard, it's not going to be simple harmonic motion. Whereas Het, he can pretty much pull it as hard as he likes, as long as the spring is strong enough and it doesn't make the thing bounce up and hit the ceiling. He's not so restricted as Joanna is. Okay, so let's try and understand these situations. So, well, it's got a bit of a diagram here to explain it to you. It tells you that if you have the mass here, you'll have a tension in the string going in that direction. And so we can resolve the mass into two components. And if we call that angle theta, which is the same as that angle theta, this would be mg cos theta, and this would be mg sine theta. So it's explained to you it's something to do with resolving the masses, but let's look at it in a bit more detail. Okay, so let's start with elastic springs and strings. If you have a ceiling here and you have a mass hanging on a spring attached to this, if you increase the force on this, the spring will stretch. And so the length will get longer and longer and longer. And if you overdo it, then you've gone past the elastic limit and it will all fall apart. But in this region, you've got linearity. And so that's what we're looking at. But what we realize is there's a bit of an offset because the spring already has a length, its original length. We call that its natural length when you've not forced it at all. So if we stop measuring L and F, and if we start instead measuring extension and force, then we get this graph here, extension and force. But then we do another thing, we swap the axes around. So we swap it so that force is on this axis and extension's on this axis. Well, that doesn't change it, you still get a straight line, and we get force is some constant times the extension. So the extension is proportional to the force, which kind of makes sense. This number K here is called the stiffness of the spring. And we're going to learn about the stiffness of the spring later on, and we're going to say it depends on the original length of the spring, and it depends on something called the modulus of the spring, and they together define the stiffness of the spring. But what we're interested in at the moment is this bit here, F is equal to K times E. So there's some simple equation. The more you force it, the more it extends, and there's a direct proportion between the two, and the constant of that proportion is just the stiffness of the spring. Okay, so let's have a look at a simple question. Okay, so somebody's got this spring. It had a length of L0, but they haven't told us what L0 is, but they've told us the stiffness of the spring. Oh, that's nice of them. They've told us the stiffness of the spring is 5G. Now they've told us when we put 25 kilogram mass on it, it stretches to 15 meters. Okay. All right, so let's go back to this equation. Force is equal to K times E. We want to use this equation. Force is equal to K times E. We want to use this same equation. F is equal to K times E. Well, if you put a 25 kilogram mass on it, 25 kilograms, then the weight is going to be 25G. So the force downwards is going to be 25G. 25G is the force downwards, equals, what's the stiffness? Well, they told us the stiffness is 5G times the extension. So the extension must be a fifth. Sorry, 5 rather. The extension must be 5. The G's cancel out. So the extension must be 5. Oh, okay. So that means the extension is 5, which means the original length must have been 10. Okay, so the original length was 10. So we work that out by it's a very simple calculation. They will give you one of these and you will work out the other one. Nothing more complicated. It's like GCSE, it's pre-GCSE stuff, yeah?
Is this part of the course, or is it mechanics?
It's mechanics, but it's relevant to differential equations. It's part of our understanding of differential equations. Look.
Okay.
systems that give rise to simple harmonic motion. So in the worksheet that I'm going to give you in pure maths, we're going to learn about simple harmonic systems, just very basically. We're not going to do any detail on them, but we're just going to have some basic understanding of what the situation is. Even this is more complicated than the situations you'll get in the worksheet. Okay, so we know that when you had it here at 15 minutes, when you had the 5 kilogram mass hanging from it, we know it was in equilibrium. It extended itself by 5 meters and it was in equilibrium. And now what's happened is Het has pulled it down a bit to X. So if he's pulled it down a bit to X, we know that when he releases it, it's going to shoot upwards. It's going to shoot upwards. We know it's going to shoot upwards. So because he's pulled it down, so his force of his hand is what's holding it down there. When you release it and you take away the force of his hand, then there's going to be a lot of force upwards compared to the force going downwards, because his hand is gone, which was one of the downwards forces holding it in that place. So what will happen is when he releases it, the forces will be, the force downwards is still going to be 5G. The force upward is going to be the tension. And we know that the tension is going to be more than 5G. And so it's going to accelerate upwards. And we know our rule is positive forces minus negative forces equals MA. What's our positive force? Our positive, well, let's define downwards as positive. Because downwards is positive, because we said that this is X. So if X is positive, then let's define downwards as positive. So our positive force is 5G. Minus, what's our negative force? Our negative force is the tension. And what's our mass? Our mass is 5. And what's our X equals 5A rather? That shouldn't say G, that should say 5A. Positive force minus negative force equals MA. Equals 5A. Okay. Acceleration is actually, well, we could call it d2x by dt squared. So acceleration, velocity is dx by dt, acceleration is d2x. What's the tension, by the way? What's the tension? Well, we know that the tension is the stiffness times the extension. Well, what's the stiffness? Well, they told us the stiffness before. The stiffness was 5G. The stiffness was 5G. The stiffness was 5G. What's the extension? Well, we know that this was 10 originally. So you've pulled it down. First of all, it's extended by 5 meters just because of the mass being placed on it. But now it's extended by another X because Het pulled it down to X. So the extension is 5 because it extended by 5 meters to get down to there, plus X. 5 plus X is the extension. So the tension is, well, the 5 meters that it pulled down because it had to balance the mass that we put on there, and then the extra X which Het pulled it down by. So the tension is 5G times 5G times 5 plus X times 5 plus X equals, hold on, did I get the mass right? The mass was 25G, not 5. The mass was 25G. The mass was 25. The mass was 25. So the mass was 25 kilogram mass, so its weight would be 25G, and the mass was 25. Okay, so 25G minus the tension equals 25A. Let's just multiply this out. 25G minus 25G minus 5GX equals 25A. Well, those two cancel out. So that gives us minus 5G times X equals 25. Remember, the acceleration could be d2x by dt squared. Let's divide both sides by 25. Let's divide both sides by 25. So that gives us minus g over 5x equals d2x by dt squared. Let's, g is 9.8. Let's stick in 9.8 divided by 5. 9.8 divided by 5. That should give me, well, 9.8 divided by 5, 9.8. It should be giving me 49 over 25. It does. Minus 49 over 25x equals d2x by dt squared. What do you notice? What do you notice? What do you notice? Joanna?
I'm not sure.
Oh, Joanna, I'm so disappointed, but
Wait,
I set it up so nicely. Look.
I missed it when you went. Oh, it's in that form.
It's in that simple harmonic motion form, and we said when we have it in that form, the answer is going to be either a sine nx, well, if it's in t, nt plus e, or a cos nt plus e. What's your n? What's your n?
Minus 49 over 25.
No, Joanna, why did you say that? You did the same thing when we were doing the integrals with the
minus 9 over 5.
Minus 7 over 5, yes, minus 7.
I mean 7, yeah.
So x equals a cos 7 over 5 t. Oh, so it's not minus 7 over 5, because the minus, you don't have to square root the minus, you just have to square that. 7 over 5 t plus e. X equals a cos 7 over 5 t plus e. Now the thing is, e tells you whether it's been shifted or not. So the normal cos graph would look like this. So it would start off at its maximum displacement, and then it would head towards 0 displacement, and then it would go to a minimum displacement, and then it would go like that. So if e was 0, then it would be the cos graph. But if e isn't 0, then it would look like this. Maybe it wouldn't start at its maximum displacement. Maybe it would start here at some displacement less than its maximum displacement. Let's go back to our actual situation. Het, when you pulled this down, remember what you did. You pulled this down. You pulled this down by x. Let's give x a number. Let's say you pulled it down by, I don't know, 2. You pulled it down by 2 meters. It's a very long spring, by the way. It's a 10-meter long spring. So 2 meters sounds huge, but this is a huge spring. So 2. You pulled it down by 2 meters, and then obviously it was quite hard to pull it down. It's a spring, yeah? They're quite hard to pull down. Using his training, his weight training, his like bodybuilder training thing. Pull it down by 2 meters, and now your hand's trembling because you got it to the maximum you can put down, and then you release it. When you release it, are you releasing it from, and its displacement is how much you've pulled it down. Its displacement is how much you've pulled it down, and even the direction in which you pulled it down is the positive direction. Its displacement is the amount you've pulled it down. So how much did you pull it down?
2 meters.
2 meters. And then you let go of it, mainly because you were not strong enough to hold on to it anymore. And then you let go of it. During the ensuing motion, what's going to happen to the displacement? Is it going to stay at 2 meters? As soon as you release it, what's going to happen?
the spring's going to go back, so the displacement will
It's going to
change.
go back. It's going to go back. The displacement's going to drop from 2. As the spring moves upwards, as the thing moves upward, the displacement's going to drop from 2 to 1 to 0. And then it's going to go upwards, because now that's what happens when you do these things. Then it's going to go to a displacement of -1. Then it's going to go to a displacement of -2. Then it's going to start coming back down again. Then it's going to start coming back down again. So it's going to go to a displacement of -1, and then a displacement of 0, and then a displacement of 1, and then a displacement of 2. That means that it's exactly like the cos graph. It's exactly like the cos graph. It's not like the cos graph with a phase shift. It's starting from 2, its maximum displacement, and then it's going down and stuff like that. So we don't need that. And A is 2, by the way, because we know the maximum displacement is 2. So there's the equation for the motion that you ensued by pulling it down. Okay. So this is the same thing, and this is looking for a pendulum. And this is Galileo's law. And this is saying to us, look, if we have a mass hanging from a pendulum, then part of that weight is acting, there's a tension in the string, and part of that weight, this is the weight, and part of that, one component of the weight, is counteracting the tension, but another component of the weight is pulling it back to the center where it started off, putting it back to its equilibrium position. So what happens here is a cruel mobster is punishing one of his henchmen. He hangs him from a 2.45 meter rope and then pulls the guy sideways and counts how many oscillations until the guy dies. Find the equation that describes the motion of the hanged man. Okay, so we know that there'll be a tension in the rope here, and we know that his weight is going to be whatever his mass is times gravity, and we know that that is going to be mg cos theta, and we know that that is going to be mg sine theta. And what we're going to do is going to say, because he only pulls it by a small amount, we're going to say that this force, which is the force that's pulling it back, that's accelerating it back in that direction, is accelerating it back towards the center, we're going to say that that force is mg sine theta. It's actually minus mg sine theta, isn't it? The force is actually minus mg sine theta, because if this is the positive direction, then the force is going in the opposite direction, so it's minus mg. But I'm going to say that that force is just minus mg theta. Can I do that? Can I just call it minus mg theta? Can I do that? Is that okay to just change sine theta to theta? Are you happy with that, Shane? Are you happy with that, Joanna? Are you happy with that? Are you happy with that, Devansh? Who's happy? Who
That's
said
the
yeah?
small angle approximation.
It's the small angle approximation, yeah. Sine theta is approximately equal to theta when theta is small, and he only pulled it a small amount. And we said right from the beginning, this only works as simple harmonic motion if you don't overdo it. Okay. Now we know that F is equal to ma, so replace that with mass times acceleration equals minus mg theta. Now the acceleration, what do we mean by the acceleration? Well, the acceleration is let's go back to here. Gosh, we're going to go back a long way. We're going to go back a seriously long way. Oh, no, maybe not that far. We're going to go back to here. What do we mean by the acceleration? We mean the acceleration is the radius times d2 theta by dt squared. So the acceleration, we know, sometimes I'm pressing the wrong button, so I'm just adding in pages the whole time. So okay, so we know the acceleration is Well, it's the radius. The radius is 2.45. So it's 2.45 times d2 theta by dt squared times the mass equals minus mg theta. And we can cancel out the mass. And so that gives us d2 theta by dt squared equals minus g over 2.45 theta. And that gives us d2 theta by dt squared equals minus g over 2.45 is a quarter, minus a quarter theta. What do you notice, Devansh? What's got you excited now?
It's in that form.
Simple harmonic motion form.
Simple, yeah. So n would be a half.
N is a half, lovely. So it's theta equals a cos. Let's get rid of that. Let's get rid of that. We didn't want that. It was just an accident. A cos a half t plus e. Now, if you start from the maximum displacement position, e just ends up as being 0. E just ends up as being 0. So it's a cos a half t. What happened to our equation? Well, okay, so both of these gave rise to simple harmonic motion. Okay, later on, when we learn more about differential equations, we'll adapt these to include damping and even forced oscillation. So that's just much, much later on. Okay, we move on. SOLDI WCC. Do you know what that stands for, SOLDI WCC? It's an acronym. What's it going to be an acronym for? Anyone?
Second order linear differential equation with constant coefficients.
Lovely. Because last week we were doing first order linear differential equations with constant coefficients, and no one wants to have to keep saying that sentence. Second order linear differential equations with constant coefficients. So having an acronym is very useful here. SOLDI WCC. Even the acronym is quite long, isn't it? It's actually a word in its own right, the acronym. Okay, so find the general solution to this differential equation. So we want to solve this differential equation. Okay, so we're going to use the same method as we did before. And the method we used before was we just imagined, we said, well, let's pretend y is equal to e to the lambda x. Then dy by dx would be lambda e to the lambda x. Really, we said it was equal to pe to the lambda x, but then we got a bit bored of having to do the p, so we just said, okay, we can't be bothered with the p. It doesn't make that much difference as long as you remember to put it back in later on. And then d2y by dx squared would be lambda squared e to the lambda x. And then if you shove all of those into this equation, you'll get, we're going to replace our d2y by dx squared with this, lambda squared e to the lambda x. So first thing I'm going to do is the thing we did last time was we got rid of that and we called it equal to 0. Yeah. And we call this our complementary differential equation. Our complementary differential equation is you just ignore the thing on the right, call it 0. Yeah, because it's easier to solve that. Then we're going to put in the these things here. So we're going to put these into here. So let's highlight them. We're going to put this one in first. So that gives us lambda squared e to the lambda x plus, now we're going to put in this one, is our dy by dx. So that gives us 3 lambda e to the lambda x. And then now we're going to put in this one, is our y, plus 2e to the lambda x equals 0. Then we divide everything by e to the lambda x, and it gives us lambda squared plus 3 lambda plus 2 equals 0, which gives us lambda plus 2, lambda plus 1 equals 0, which gives us lambda equals minus 2 and lambda equals minus 1. This all is exactly the same as we got last time, except last time we didn't get 2 values of lambda. We only got 1 value of lambda, and last time we would write y equals pe to the minus 2x. We just have one of those. But now we have to write y equals pe to the minus 2x plus qe to the minus 1x. because we get 2 values of lambda. That's it. That's the only difference. We get 2 values. That's it. That's no big deal. So this is called our complementary function, and it doesn't solve the original differential equation at all. It does not solve this at all. It doesn't solve this at all. It solves this. But that's us cheating, because we can't change it and get rid of the 0. So what we then do is we say, no. Okay, right, let's go back to what it should have been. So we go back to what it should have been. And now we're going to guess a particular integral. So let me just copy that. Or just slide it down here. Now we're going to guess a particular integral. So a particular integral for this would be y equals, I don't know, let's try ax plus b. And then we have to do dy by dx and dy by dx squared, and then it all becomes exactly the same as the last time. Okay, we're going to do an example of it. So it hasn't changed what we do one bit at all. Okay, so this is the same question. We know that our complementary function was y equals p e to the minus 2x plus q e to the minus x, because that's what we got here. And now we're doing our particular integral. Our particular integral, well, look on the right-hand side, we've got 8x. Which does that match? That matches this one. So our particular integral is going to be of the form ax plus b. Okay, so let's try, so y is going to be ax plus b. Y is going to be ax plus b, which means dy by dx is just going to be equal to a. See how I've lined it up? So it's underneath the constants. And d2y by dx squared is just going to be 0. It's just going to be 0. And then what I'm going to do is I'm going to say, yeah, but my differential equation had d2y by dx squared, sure. But then it had 3 dy by dx. It had 3 dy by dx. So I need to triple this equation. So let's just triple that equation. Let's times that by 3 and times by 3. And then also mine had 2 lots of y. So let's just double that as well. So double that, double that, double that, and double that. And then when we add these together, when we add these three together, it's going to give us 2ax plus 2b plus 3a. But hold on. When we add these three together, it has to equal 8x. It has to equal 8x. Match up the coefficient of the x's. So 2a has got to equal 8. And so a has got to equal 4. So I know a has got to equal 4, so that's 12. Match up the coefficient of the numbers. Well, there's a 0 here, and there's a 2b plus 12 here. So 2b plus 12 has got to equal 0. b plus 6 has got to equal 0. b's got to be minus 6. And so my particular integral, a is 4, b is minus 6. A is 4, b is minus 6. b is minus 6. And so my general solution is join these together. My general solution is join these together. So that gives me y equals p e to the minus 2x plus q e to the minus x plus 4x minus 6. There's my solution. Whoa, I didn't want to do that. Go away. Okay. All right. Okay, now we're on a different page. On a page from like ages ago. Okay. It's a little bit of time traveling as well there. Okay. So there's our equation, and we can check it, but not with this calculator. Not with this calculator. You know why? Because those mean Casio scum people, I met them actually when I went to the EdXL conference, so I better take that back because they're obviously not mean. well, they slightly are, but they didn't put a d2y by dx squared button on it. They could have done easily. It wouldn't have been hard for them to do that. It wouldn't have been at all hard for them to do that. They didn't want to do it because they want to sell you the big fat graphic one for 120 quid. Well, it's not 120 quid, but you get what I'm saying. They're profiteering at your expense. But if you happen to have the big fat graphic one because you don't mind being profiteered at your expense by Casio, then what you can do is you can check it because it has a d2y by dx squared button on it. And so what you can do, and it shows you on the website how to check these if you happen to have those calculators. Do it. If you've got that calculator, that's the biggest advantage of it, is you can check your second order differential equations as well. Okay, let's move on, because as we can guess, there's going to be more than one case. So, right, how do we do this now quickly? Well, this one is straightforward, because this one, we don't even have to cross out this right-hand side to get our complementary differential equation, because they made it 0 already. How lovely was that of them? So what I'm going to do is I'm going to go straight into substituting y equals e to the lambda x, but I know what it's going to give me. It's going to give me lambda squared minus 4 lambda plus 3 equals 0. Lambda squared minus 4 lambda plus 3 equals 0. So it's basically this number, and this number that I'm looking at. So, and that gives me lambda minus 3, lambda minus 1 equals 0, which gives me lambda equals 1, lambda equals 3, which gives me y equals p e to the x plus q e to the 3x. And there's my answer. Job done. There's no particular integral to find. There's no particular integral to find. Okay. What about this one? Well, this time they have put in the e, they have got a right-hand side. So I will first of all have to just delete that to get my complementary differential equation. And then I'm going to do 2 lambda squared minus lambda minus 3 equals 0. You can see where I got those numbers from. The 2, the minus 1, let's just put in a 1 in there. Let's just put in a 1 in there. And the minus 3. You can see where I got those numbers from. And that's equal to 0. So that gives me 2 lambda, and that gives me lambda, and that gives me a 3 minus 3 and a plus 1 equals 0. And so that gives me lambda equals 3 over 2, lambda equals minus 1. So that gives me y equals p e to the 3 over 2x plus q e to the minus x. Okay, that's my general solution. But this time I have to do the particular integral thing. I have to do the particular integral thing. So look at this, then look at the right hand side here. That looks like that one. My guess is going to have to be a e to the px. Okay, what I'm going to do is I'm just going to pull this down to here, so I've got a bit more space to work with. So it's going to be y equals a e to the 2x is my y. So what's my dy by dx going to be? My dy by dx is, well, if you differentiate that, it just gives you 2a e to the 2x. And what about my d2y by dx squared? What's that going to be? Well, that's just going to be 4a e to 2x. Wow, they were so easy to differentiate. Okay, but hold on. I've got 2 lots of d2y by dx squared. So I need to double this equation here. So let's double that. Times that by 2. Times that by 2, that's going to become an 8. Let's just change it to an 8. Okay. And what about this one here? I've got minus 1 dy by dx. So I need to change this one into a minus 1 dy by dx. So let's put a minus in front of that and a minus in front of that. And then the last one needs to be a minus 3 times y. So let's just put a minus 3 in front of there and a minus 3 in front of there. Now, when I add all of these up, then it gives me 2 d2y by dx squared minus 2y by dx minus 3y, which is all of that, which is e to the 2x. So that gives me e to the 2x equals, and what do I get here? I've got 8a e to the 2x minus 2a, so that's 6a e to 2, minus another 3, that gives me 3a e to the 2x. And so that cancels with that. That gives me 1 equals 3a, a equals a third. And so now I know that my particular integral is y equals, well, it was a e to the 2x, but a is a third, so a third e to the 2x. And so my general solution is y equals p e to the, what was it, minus 3 over 2, no, it was 3 over 2, p e to the 3 over 2 x plus q e to the, was that a minus x? Yeah, minus x plus a third e to the 2x. Okay, and so there's my equations of. It's exactly the same as we were doing in the last exercise. Sure, you've got one more differentiation to do here. Big deal, yeah? It's exactly the same as what we were doing in the last one. Okay, let's do one more. d2y by dx squared minus 25y equals sine 2x. So let's cross out the right-hand side, put that equal to 0. So we've got a complementary differential equation. Lambda squared minus 25 equals 0. Lambda equals plus or minus 5. And so y equals p e to the 5x plus q e to the minus 5x. There's my general solution. Right, let's go back to here. Let's look at this and tell us what form we got to have. It's like this. So it's going to be this one. So it's going to be, well, my q is 2. My q is 2. So it's going to be a cos 2x plus b sine 2x. Okay, right, fine. It's a bit more of a messy one, but that's all right. I'm not fast. Differentiation is easy. So this will be easy. So we've said that the particular integral is of the form y equals a sine 2x plus b cos 2x. Doesn't matter which way around you write them, nobody really cares. Okay, but we're going to need to find dy by dx and d2y by dx squared. Actually, I don't need the dy by dx, but I have to work it out anyway to get to d2y by dx squared. So well, then that's not saving me any time. dy by dx. Okay, differentiate a sine 2x. It gives you 2a cos 2x. So 2a cos 2x. You notice I write it underneath the cos 2x. Of course, it makes sense to write it there. And differentiate the b cos 2x. It gives me minus 2b sine 2x. Okay, now I need to differentiate again. d2y by dx squared. Differentiate the minus 2b sine 2x. That's going to give me minus 4b cos 2x. Minus 4b cos 2x, and differentiate the 2a cos 2x. That's going to give me minus 4a sine 2x. Right, okay, what have I got? I've got a d2y by dx squared, just one of them, so that's fine. That matches with what I've got there. I don't have this at all. I don't have this at all, so let's just delete that. Let's just get rid of that. And then I've got minus 25 of the y. So this y, I've got minus 25 of them. I've got minus 25y. So I need to multiply by my y by minus 25, which means that becomes minus 25, which means that becomes minus 25. And then I'm going to add them all up. So d2y by dx squared minus 25y gives me that, which is sine 2x. Sine 2x equals, now I've got to add this up. So that's going to give me minus 4a sine 2x minus another 25. So that's going to give me minus 29a sine 2x. And then I'll add these two up. So that gives me minus 4b cos 2x minus 25b. So that gives me minus 29b cos 2x. Okay, let's match it up. Well, this has just got a 1 in front of the sine 2x. So matching up the terms, that's the sine 2x term, that's the sine 2x term. So that tells me that 1 has got to equal minus 29a. And so a has got to be minus 1 over 29. Hold on. Yeah, minus 1 over 29 is a. And B's got to be 0 because this is the cos 2x term, but I don't have a cos 2x term on my other side. So B has got to be 0. So B's got to equal 0. And so my equation is -1/29 A. So -1/29 sine 2x. So y equals -1/29 sine 2x. That's my particular integral. Add it onto my general solution, and I will get add it onto my my complementary function. Add it onto my complementary function, and I will get my general solution. Okay, now we need to move on to some slightly harder questions. So let's start off with this. d2v by dx squared equals 0. Help me solve that. It's not hard. It's not hard. Help me solve that, Joanna. An A-level student. Probably a GCSE. Carry on.
So I just differentiate it.
You just integrate both sides. You want to solve it, so you integrate it.
dv by dx. Yeah. And then equals c. Yeah.
You haven't solved it. We need to get to v.
And then time.
Integrate it once more.
V equals c.
It's with respect to x that you're integrating it, yeah?
Yeah.
So v is dx plus d. So that leads you to v equals cx plus d. That's not supposed to be interesting or complicated. It's just pointing out that if you have d2v by dx squared equals 0, it's going to give you v equals cx plus d. Okay, differentiate this twice. So off you go. Differentiate this twice to Shane.
So isn't that like, didn't we do that before and then you went
Yeah, well remembered. So we've got d2v by dx squared equals e to the minus px, d2y by dx squared minus 2p dy by dx plus p squared y. So I'm just pointing this out in case we ever see this, in case this ever crops up. In case this ever crops up. In case this ever crops up, I'm just pointing it out so that we know that that would be this if you integrated it. If you integrated it, it would be that, because we differentiated it to get to that. So just in case it happens, it won't happen, but just in case it happens. Okay, now we want to solve this one. So what we're going to do is we're going to start by saying let y equal e to the minus 4x. Let y equal e to the minus 4x. And I mean, really, I should say let y equal e to the minus lambda x, but I've just chosen lambda as being minus 4. And the reason I've chose lambda as being minus 4 is because that's a minus 8. So I just thought, well, that would probably work if I chose minus 4, yeah? So, okay, off you go. Okay. So off you go. So that will give me dy by dx equals minus 4 e to the minus 4x. Actually, you know what I'll do? I won't do it this way. I'll do it that way, so we can use what we did before. Let's do it like this. Let's do v equals e to the minus pxy. Let's do let v equal e to the minus 4x times y. And then let me ask you what d2v by dx squared is. I will bring that answer back for you. So let's try. in case you need it. So I've said let v equal e to the minus 4xy. You had this. You had that, and it gave you this result. But I've said to you, can we make v equal e to minus 4xy? And I tell you where I got the 4 from. I got it from here. The minus 4 rather. Sorry, can you just differentiate that twice for me really quickly in your head? To Shane.
E to the power minus 4x d2y by dx squared minus 8 dy by dx plus 16y.
Now you know that for this question, this is equal to 0. I mean, this is equal to 0. Well, that's this. It's the same as that. And for your question, that's equal to 0. So for your question, d2v by dx squared equals e to the minus 4x brackets, and then all of this is 0 for your question. It's 0. It's equal to 0 for your question. Okay, so that gives you d2v by dx squared equals 0. Can you solve that for me, Joanna? d2v by dx squared equals 0.
First, when you integrate, you get dv by dx and equals c.
Yes.
And then v equals cx plus d.
Lovely. V equals. Now, I hope you won't mind, but I'll use px plus q, which is just different letters, isn't it? Okay. Now, so we've found out that v equals px plus q, but hold on. V stood for this, e to the minus 4xy. So e to the minus 4xy equals px plus q. And so y equals e to the 4x brackets px plus q. So that's the solution to this differential equation. So that's the solution to this differential equation. It's y equals e to 4x px plus q. But why? How comes what we did before didn't work? Why can't we just do it the way we did it before? The way we did it before was lambda squared minus 8 lambda plus 16 equals 0, which gives us lambda minus 4 equals 0, which gives us lambda is 4, which gives us y equals pe to the 4x. Now the reason that doesn't work is you're supposed to get 2 answers, aren't you? Otherwise, it's like the first order differential equation. The second order one is supposed to give you lambda equals 3 and lambda equals 2. You're supposed to get 2 answers. So what happened with this question is the quadratic equation that it gives you, it's called the auxiliary quadratic equation. The auxiliary quadratic equation it gives you doesn't have 2 separate answers. So if that question doesn't have 2 separate answers, then you only get 1 answer. Then that's not a complete enough answer. That's not a complete enough answer. So the second bit of the answer is actually this bit here. You have to multiply by px plus q. Now that we know that, we don't need to worry about redoing it this method every time. Now that we know that, we can just say this is the new rule. The new rule is if you only get 1 repeated root, which is alpha, then the solution, the general solution, the complementary function is going to be e to the alpha x brackets px plus q. So if you only get 1 like we did in that, now we know that we don't need to do it that slow way anymore. So now, if we get a question like this, we can just do it the same quick way as we did it last time. We can just do it as 4 lambda squared plus 4 lambda plus 1 equals 0. Remember, I'm ignoring that to start off with. And so that gives us 2 lambda plus 1 2 lambda plus 1 equals 0. That gives us lambda equals minus a half. It only gives us one solution. So the rule when we get one solution is y equals e to the minus a half x brackets px plus q. So that is our complementary function. That's our complementary function. We still need to find the particular integral, and it's exactly the same way to find the particular integral as before. So for 3x plus 4, our guess would be 3x plus 4 is this one, isn't it? So it'd be ax plus b. It'd be ax plus b. So I'll do it, but I might stop doing it after a little while because these are so easy. These. So y equals ax plus b. dy by dx equals a. d2y by dx squared equals 0. I need 4 d2y by dx squared, but then that's still just going to be 0. I need 4 dy by dx, that's going to be 4a, and I just need 1y, and I need to add them together, and then it should equal, all of these together should equal 3x plus 4, and that equals ax plus 4a plus 3. Well, that's the unit, so that's got to be 3, so a's got to be 3. That's the x term, so that a's got to be 3. And then that's the unit, so 4 has got, oh, hold on, I know a is 3, so if a is 3, that's 12. So 12 plus b has got to equal 4, and so b has got to equal minus 8. And so my equation is y equals e to the minus a half x brackets px plus q plus ax plus b. A was 3, x minus 8. And so there's my final answer. That's my general solution. Okay. Can you solve this equation for me? Can you solve this equation for me, Devansh?
Isn't that the simple harmonic?
Yeah.
So that would make I haven't written down the thing.
A cos nx plus e, or if you want, you could expand this by doing the compound angle expansion, and you could call it v equals p cos nx plus q sine nx. Remember, we're going to use both of these versions, so remember that they do coincide with each other. You can write it like this, and you can write it like that. Differentiate this twice. Well, we've done that. Why do they keep asking us to do that? Here, we did it. Here's our answer for it. Oh, we lost it. Never mind, we can write it out again. We know what it was. Gosh, it's quicker just to write it out again, isn't it? And write it again. So differentiate that. So that's d to v by dx squared equals e to the minus px d to y by dx squared minus 2p dy by dx plus p squared y. Let's highlight it. And let's save it because it's going to be useful to us. Group, cut, paste. Okay, shove it on the side. Okay, right, so I'm going to do the same thing again. I'm going to start off with y equals, I'm going to halve this number, so e to the minus 2xy. Okay, so I'm going to halve that number, and I'm going to do e to the minus 2xy. And I know e to minus 2 p equals e to the minus 2xy.
So can't you just do it lambda squared minus 4 lambda plus 5 equals 0?
I can, yeah, I can. And I will.
Yeah.
So I'm doing the same thing as we did here, which was v equals e to minus pxy. And I'm doing v equal, oh, sorry, I've got p, not p. V, rub that out, change that into v. V equals e to the minus 2xy. And but I know that the rule for e to the minus pxy is this rule here. So when I differentiate this, it gives me, if I differentiate this twice, it's going to give me Devansh? Devansh, have you died? Do you still exist, Devansh? Okay, we lost Devansh. It's sad, but it happens. Okay, so okay, so differentiate this twice for me, Joanna.
Wait, is it, what respect is it?
It's,
oh wait, you already did it.
You can use this. It's with respect to x.
Minus p e to the.
No, you don't need to do any of that. I've already done it for you here. I've done it for any situation, e to the minus pxy. I've done it for any situation, e to the minus pxy. And I've asked you to do e to the minus 2xy, and I've already done it for p, so you just need to make p too. You don't need to do it. My God.
So sorry, Sam, you started buffering. You froze, and I didn't really notice.
I froze. Okay. Sorry.
Yeah.
I am a bit cold, but I didn't mean to freeze. That's because the heating switches itself off in this room. Okay. Go on, Joanna.
Minus p
No,
e to the minus p.
It's just this. It's just this. See e to the minus pxy. When you differentiate it twice, you get that. But you've got e to the minus 2xy. Like all I've done is change the rule with c.
Okay. Yeah. E to the minus 2x, and in brackets, d. I think this is d2y.
Oh, it's hard to read, isn't
squared.
it? Sorry.
Yeah. Minus 4. Yeah, minus 4 dy by dx plus 4y.
I'm going to write it as 5y. I know you said 4y, but I'm going to write it as 5y. I don't care what you say. Okay, I do care what you say. I changed it back to 4y. Okay, so, oh, but hold on. This matches this. And so we know that that's equal to 0, so we can just put in 0 instead of there. So d2v by dx squared equals e to the minus 2x times 0 minus y times, well, just times y times minus y. Times minus y. Okay. Just try and tidy that up because it's gone a bit rubbish there. Okay. Hold on. Isn't that just that? It is, isn't it? Yeah. I'll just substitute it in then. I don't care. d2v by dx squared equals minus v. d2v by dx squared equals minus v. Let me rewrite that. d2v by dx squared equals minus 1v. Devansh?
Hi.
Hi.
Oh, yeah. Simple harmonic. So ends 1.
So v equals a. Should we do this one? Should we do this one? You can do either. Let's do this one. It'll be more fun. V equals p cos nx plus q sine nx. What's your n again? You said it was 1, didn't you? So
Yeah.
v v equals p cos 1x plus q sine 1x. Okay, so that's the answer. We know that's the correct answer. Okay, v stood for e to the minus 2xy. So e to the minus 2xy equals p cos x plus q sine x. And so y equals e to the 2x brackets p cos x plus q sine x. That's a different answer again. Wow. Wow. I mean, we've got the e to the something x like we always get. We always get an e to the power something x. But now we've got this like weird p cos x plus q sine x. You said don't do it this way. You implored me. You pleaded with me. You said please don't do it this way. Do it the normal way. Do it the normal way is, well, that's just lambda squared minus 4 lambda plus 5 equals 0, which gives me lambda minus 4 lambda minus 1 equals, oh, it doesn't factorize. It doesn't factorize. Oh, crap, it doesn't factorize. All right, let's try completing the square then. Lambda minus 2 squared plus 1 equals 0. Lambda, so that's, we're going to have to take the 1 over the other side. We're going to get minus 1. We're going to square root it, so it's going to give us complex solutions. Lambda equals 2 plus or minus 1i. Is going to be our solutions. 2 plus or minus I is going to be our solutions. Well, look, there's the 2 there. There's the 2 there. There's the 1 in front of the I became, oh no, gosh, where are we now? We've lost our page. We're further down than that. We're further down than that. Okay, we must be about here. Okay, so oh, what's it doing now? It's hiding the pages. Okay, so what we've discovered is when you get complex solutions in the form p plus qi, so ours were in the form 2 plus or minus 1i, then the equation is going to be y equals e to the 2x p cos 1x plus q sine 1x. So now we know that result, we can just apply that result each time. Okay, so say we get something like this. We just go lambda squared minus 2 lambda plus 50 equals 0. Lambda minus 1 squared plus 49 equals 0. Lambda equals 1 plus or minus 7i. So the equation is y equals e to the 1x p cos 7x plus q sine 7x. I'm trying here. I'm trying my hardest. Okay, so this is a question which, so this is now sort of putting the whole lot together. So here we've got d2y. So first thing we're going to do is put that as being 0. And then that gives us lambda squared minus 4. Lambda plus 3 equals 0, which is lambda minus 3, lambda minus 1 equals 0, lambda equals 3, lambda equals 1, p e to the 3x plus q e to the x. Now we're going to look at this. Now we're going to look at this. Let's just, now we're going to look at this. It looks like this one here. And so our particular integral is going to be a cos 2x plus b sine 2x, because ours is 2x. So So it's going to be a cos 2x plus b sine 2x. And then it's going to get a little bit messy. So y equals a sine 2x plus b cos 2x. And then we're going to do dy by dx equals, differentiate that, it gives us 2a cos 2x, 2a cos 2x. Differentiate that, it gives us minus 2b sine 2x. Do d2y by dx squared, differentiate it again, d2y by dx squared. Differentiate that, it's going to give us minus 4b cos 2x, minus 4b cos 2x. And then differentiate this one, it's going to give us minus 4a sine 2x, minus 4a sine 2x. Okay, let's look at our differential equation. It had 1 in front of the d2y by dx squared. So we just need one of these. So we just need one of those, which we've got. Then it had 4 in front of the dy by dx. It had 4 in front of the dy by dx. So we're going to have to multiply this one by 4. So that's going to give us minus 8. And then that's going to give us 8. And then in front of the y it had 3. So that's going to give us 3. And that's going to give us 3. And then we need to add these 3 up. Oh, hold on. It was a minus 4. It was a minus 4 in front of the dy by dx. There's a minus 4 in front of the dy by dx, so that's going to become a plus, and that's going to become a minus. Okay, now we're going to add these up, so it's going to be d2y by dx, we have minus 4 dy by dx plus 3y, but that's got to equal that. So it's got to equal 10 sine 2x plus 15 cos 2x. But what do we get? We get 3a minus 4a and then plus 8b. So we get 8b minus a, lots of sine 2x. And what do we get for the cos 2x's? We get 3b minus 4b minus 8a. So that gives us minus 8a minus b, lots of cos 2x. And so that gives us, well, the number of sine 2x's has got to be 10. So 8b minus a has got to be 10. And the number of cos 2x's has got to be 15. So minus b minus 8a has got to equal 15. I can multiply through by minus 1. So b plus 8a has got to equal minus 15. Okay, so let's try b equals, I mean, you can solve it using your simultaneous equation solver on your calculator. I'm just going to guess b is 1 and a is minus 2. That might work. 8 and minus 2 will give you 10. And b is 1 and minus, yeah, it works. Oh, okay, that was cool. So my equation is, my particular integral is y equals 1 sine 2x minus 2 cos 2x. And so my general solution, you've got to join this and this up and this up. So my general solution is y equals p e to the 3x plus q e to the x plus sine 2x minus 2 cos 2x is my solution. If you've got something like this, you're going to do it exactly the same, except start off by making that 0, lambda squared minus 8, lambda plus 16 equals 0, lambda minus 4 squared equals 0, lambda equals 4. We know that gives you y equals e to the 4x px plus q, and then you need to also find your particular integral. For your particular integral, you will start with x squared plus 1 ax squared. We'll start with this, ax squared plus bx plus c will be our guess. Next one, you're going to start by making this 0, lambda squared plus 3 lambda minus 10 equals 0. That gives me lambda and my plus 5 and minus 2 equals 0. And so it gives me lambda equals -5, lambda equals 2, y equals p e to the -5 x plus q e to the 2x. And then for your particular integral, you're going to guess 3e to the x. You're going to guess ae to the x. Now, luckily, ae to the x does not merge with either of those. If it did, we'd be in trouble and we'd have to change our guess. Next one. Again, I'm not finishing it off. Lambda squared minus 7 lambda minus 10 equals 0. And so that's going to give me lambda and lambda. And then that's going to give me 10 is 5 and 2. Minus 5 and minus 2. No, that doesn't work. That'll give me plus 10. Let's try lambda. It doesn't factorize, does it? So if it doesn't factorize, then what will be my next thing to try? Could try completing the square. Lambda minus 7 over 2 squared minus 49 over 4 minus 40 over 4 gives me 89 over 4. And so we can complete the square. And so that gives us lambda minus 7 over 2 squared minus 89 over 4 equals 0. And then that gives us 89 over 4 equals lambda minus 7 over 2 squared. And then square root both sides gives me 89, gives me root 89 over 2 plus 7 over 2. And so we get surds, but the surds don't make any difference. We work it out in exactly the same way. Lambda squared plus lambda plus 1 equals 0. It doesn't factorize. Lambda, lambda plus 1 plus 1. It doesn't factorize. Okay, what should we do? Let's try completing the square. Lambda plus a half squared plus 3/4 equals 0. That gives me lambda equals, so if I take that over to the other side, I'm going to get minus 3/4. So when I square root that, it's going to give me root 3 over 2i minus a half plus or minus root 3 over 2i. So y equals p e to the minus a half x brackets p cos root 3 over 2x plus q sine root 3 over 2x. And then my particular integral is, oh gosh, look at this one. Ah, right. Okay, so the trick with this one is the particular integral. We don't have a particular integral for that. Here's what my first guess would be, and I'd hope it would work. Y equals cx e to the 3x. If that doesn't work, my second guess would be y equals cx plus d e to the 3x. Put that as 0. Lambda squared plus 9 equals 0. Lambda equals plus or minus 3i. Y equals e to the oh, so we didn't normally, we get like 0 plus or minus 3i. So here this is more like the simple harmonic motion. I mean, we can write it as e to the 0x brackets p cos 3x plus q sine 3x, but maybe we should just treat it as a simple harmonic motion one. Lambda squared equals minus 9, so lambda equals plus or minus 3i. So that would be y equals a, well, we'll use p cos 3x plus e. So we can just use the simple harmonic motion one straight away, rather than using the a cos, because it came out like the simple. I mean, you can do it like that, because the e to the 0x would just be 1 anyway, and the p cos 3x plus q sine 3x, you could do the compound angle transformation and rewrite it like that. Okay, this is just to show you, you can extend this lambda to the 4 minus 2 lambda cubed plus, sorry, minus lambda squared plus 2 lambda equals 0. And then just type it in your calculator. Menu equation polynomial degree 4. I've got a 1, I've got a -2, I've got a -1, I've got a 2, and I've got a 0. It tells me the answers are 2 and 1 and 0 and -1. Okay, fine. So y equals c e to the 2x plus, no, p e to the 2x plus q e to the x plus r e to the 0x would just be r plus s e to the -x. And so those are my answers. Okay. That's your homework, exercise 7.23, 7.24. If you've already got those exercises from the old worksheet, re-download the new worksheet. So to re-download the new worksheet, you've got to tell your browser to clear the history. Otherwise, it will think it's already got the worksheet, and when you think it's downloading it, it's not. It's just giving you the old worksheet again. So re-download the new worksheet.